the goal for today's meeting is also preparation. We will prepare several meetings, and then finally I will dump the whole theory in one meeting. But why this preparation goes so long? Because we need to change our mindset. We need to start thinking about excited states, which are quite different object than regular ground states. And if I summarize what we will do today, it's so easy and so complicated. So if I can try to summarize it in like one sentence, but it will not make sense. And to chat about it, it will maybe take over time. We will need to introduce concept of so-called transition density. And I even do not ask, have you heard about it? Even if you did, it is quite counterintuitive thing that is really helpful, but counterintuitive. So everything we did before were densities that we can plot that corresponds where all electrons are. And transition densities is an object that describes pathways, how electron goes from one state to another one. And unlike the total density, which is like special function of one variable, one of three Cartesian coordinates, the transition density is function of two coordinates, if we want to describe it as coordinate. Or if we speak on the language of matrices, then regular density corresponds to just occupations of orbitals, which is like a vector of numbers. And transition density will be matrix, telling how we go from one orbital to another one to another, like all pairs of orbitals. And if you feel comfortable with this concept, then we are done for today. I will be mumbling about it again and again from different aspects. And when I will be done through the part about transition densities, I will just go over summaries of little tricks related to the projects and to description of optical absorption. Okay. So screen. So we are approaching to most interesting part of the class, to the projects, and eventually some of the projects will be possible to compare with experiment. Recordings of lectures and labs from previous years are all available. And previous years, there were some attendees who didn't decide which project to do. So I was advocating and suggesting several projects until the last moment. But with great luck, I think everyone knows the subject to explore. So we did discuss this little chart last time. So, and the modifications could be substantial. It's only how to say, the general trends, what to do if you do not know what to do. So select model, optimize geometry, characterized by density of state and spectrum, then practice molecular dynamics, find again density of state and spectra, and compare. So I already got emails asking, like, do I need to practice molecular dynamics for my model? What do I learn from it? And those are legitimate questions. So do not hesitate to ask questions either to yourself or to me. So this is not like, it is universal, but not mm, sharpened for each individual project. And it's possible to accumulate a lot of information, but please try to be directors of your own project. So think about what new question your research can answer, and select tools based on necessity to help to answer your question. So we are trying to mimic real life when research is done only for novel things. If answer to your question is known, then there is not much reason to do research, only educational. So the main goal is to try to find such problem where you really can do something novel. Right? Well, it's not ready. It's already starting where we left off. So please show me if you remember the slide from last meeting, you don't remember, or you have seen it, but you have no idea what it shows. Yes. Cup of coffee. Yes. Yes. Cup of coffee as an answer is good. And another thing I learned from you is like showing like, little yes. So I'll repeat quickly, but we'll go to the next stage. It's simple thing, but I hope well, I have proofs through your homeworks that you have done it. So generally, density is a function of one electron, and it runs until highest occupied. We can replace this highest occupied with infinity, and then we need to set up population function or occupation function, which will be once one if you go from orbitals from one to HOMO and zeros otherwise, right? And this occupation function, F probably stands for Fermi or in Enrico Fermi, can be manipulated by the Fermi command, where one promotes electron from one of the originally occupied to one of the originally unoccupied. Typically, in the homework, you were taken from HOMO to LUMO, but one can do some other promotions of electrons. So rigorously speaking, it is not true excited state. It is roughest approximation of excited state. And we are doing it because it is so cheap and quick. But if in the community of computational chemists, you are speaking of excited states, it is something different. So if you want to speak about this Fourier, one always needs to like make a disclaimer and apologize so that my system is so big, I need to make approximations. So next step, which I think we didn't cover. In the previous slide, we used, no, it's too quick. It's too quick for me. So this is orbital number I, absolute value squared. Or one can write it down as pair of orbitals, orbital number I and the same orbital number I, with and without star, right? So by now, it doesn't surprise you. And now let's make a generalization. What if I will use different index here? So let's discuss, because it is a key step. The thing will roll over after. So what should I do to keep the same density if I want to, just by frivolously use different index here. Let me ask Kea. So it's mathematical question, nothing with
Yeah.
So what should I do? What should I do to allow such manipulation? Do I need to add another factor or change summation? Like if I want to use different indices for this pair of orbitals.
We need to add something here.
Uh-huh.
Because there you use before it was I means there. Now you use another it's factor or something. Well, I don't know the name.
It's different index, different orbital.
Different index. So we need to another function for that.
Okay. Yep. Thank you. Thank you.
Or if it possible, like I forgot, I saw something like Fij, and the function is one, but it defined as like Fij, means
yes.
someone like
Yes,
this.
we need an analog of this f function, but we your answer absolutely correct. So thank you, Lola. Would you like to comment on continue this discussion?
Okay, I'm not sure.
The answer is no. I do not want.
No. Okay, I'm not sure that I understood the question. Please, can you say
Okay.
that?
Okay. Let me repeat. So originally, we had a mathematical expression where we had two orbitals and both of them were having index I. And we were making summation over this index I. And now only as a mathematical game, just as a, I want to replace index I to a different letter, to put different letter. Which adjustments I need to, how should I fix the rest of the equation so it will be equal to the same result? Does it make sense?
Yeah. You want to get the same result, but you want to tweak the subscript of the. Something about the.
So K
I think
told
it's
that,
F.
huh? Yes, F is good, but we need to.
Professor, like there in the below in the summation section, we need to define it like this way. It means in a mathematical way, like summation, some one thing. It's because there is Ij. Okay, you already define it Ij. So there is another way, like you no, it's okay Ij. Then you need to define it like Fij. Yeah, and that's
Yes, exactly. You need to do Fij. Yes, yes. Yeah, thank you, Kia. And Lola, would you please continue? Like, what should be the properties of this Fij to allow this blue J?
The property.
So we originally we included only pairs when I equals J, right?
Yeah.
And now
I
we want to have the equal sign here. So when I is not equal J, when I is not equal J, we want to multiply everything by 0. Make sense?
Yeah.
Okay, so we can put here the delta function ij, which is exactly a symbol which is equal 1 if I equals j and 0 if I is not equal j. Make sense?
Yeah.
Okay, yeah, thank you. And this is probably the most intellectually challenging step. The rest will be based on it. So here we are defining density as by constructing it from the pairs of non-coinciding orbitals. Instead of function f, we will call the factor here with letter, again, letter rho, because here is density. Here we speak also about density, but the dependence on position will be hidden in orbitals, and this factor does not depend on position. It depends only on indices. An object with two indices is typically a matrix, right? So this will be a matrix for density, or one can call it density matrix. Okay? No one or anyone is against it. Probably not, because it's just definition of the name, right? And we can agree that in case we describe ground state, so this universal formula should work for ground state as well. For ground state. For ground state, we need to take into account only such pairs of orbitals where I equals j. So we need to put here 1 if I equals j and 0 if I is not equal j. And also we need to put 1 only if this I and j are smaller or equal to homo. Then this definition of density will agree with the one that we used in traditional DFT, with ground state DFT. And this condition to have ones and zeros can be written this way. Maybe. So it will be 1, 1, 1 until we meet homo. So on the main diagonal it will be ones, and then on the off diagonal we will have zeros. 0, 0, 0. And then everywhere apart from this lowest indices block, everywhere except this part, it will be zeros everywhere else on the diagonal and off diagonal. So all elements will be zeros. So this is general density matrix suited for the ground state. So by setting up density matrix in this way, we still can practice ground state DFT. Make sense? Please protest or ask questions so that I do not go too far without we do not lose anyone in this discussion. Or you can tell them that I'm already lost. Okay. So I think it is absolutely the same thing, just with my ugly handwriting. Yes, Fermi Dirac for regular DFT. Okay. I need to apologize. It's truly ugly, and I promise to myself to improve it from year to year. But although ugly, it is correct. So I see who was looking with tight interest. Kea, would you like to say what do you see on this in this spot in this area?
Yeah, it's like we did a homework like this. This type of things was there. So we need to that one was the integration, and there is summation. So if I and j both are same, then that it would be the like 1, and if there is same indices, then it will be 1, then another one if like 0, like this way. And like if I miss anything.
Okay, okay, yep, everything is correct, but we can add a little bit more. Yeah, thank you, Kate. Lina, will you please comment what you see and how you interpret?
Okay, so I see here the density of the electron is depending on two states. And in the first one, we have ground states path. There's no transition. But in the second and third, there is transition between the ground state and the excited states. So this is how we calculate the density depending on the state function and the density function with the indices I and j.
Okay, yeah, everything is correct, and I'm very happy. But there is one more side that I would like to add, or maybe ask someone to add. So I'm returning back a couple of slides. Okay, so Sarah, may I ask you to try? So what can you say about limits of these summations?
About what?
About limits of these summations. So what's the minimal and maximal value of the summations in this definition?
And I think the maximum maybe it should be homo for the ground state.
Okay, but if it is not ground state, it goes from 1 to infinity, right?
Yes.
But you were absolutely correct about saying that if it is ground state, it should go up to homo. So let me maybe insert new slide. I'll delete this little things. So we have summation number 1 from I1 to infinity, and then some summation over a second index j from 1 to infinity. Now Sarah told that for ground state we need to perform summation for the from 1 to homo, right? But if we want to be general, we need to continue summation. So we can put summation of all other terms that we originally didn't include. So I continuing from luma to infinity. Make sense? So we replace this summation by a bracket, and then the second summation can be replaced in a similar way. So summation of j from 1 to homo plus
j equal to luma to infinity.
Yes, exactly, from luma to infinity. And then after these two summations, we put rho I j theta I star theta j. Not phi, theta. Make sense? Okay. And now another little trick. Thank you, Sarah. Let's do. Everyone does a little bit. The reason that Sarah has suggested for this expression is that we should consider orbitals below HOMO and above HOMO on different range, because below HOMO are really important and above HOMO sometimes they need, sometimes no. Right? Now, what if I'm really emotionally attached to summation from 1 to infinity, but I still want to take into account difference for orbitals below HOMO and above HOMO? Does the question make sense, or completely no sense, or you need more explanation?
Doctor, can you please just repeat the question? Thank you.
So, what if I need to account differently, to account differently orbitals, contributions of orbitals below HOMO and above HOMO, or equal to or above LUMO, on one hand. On another hand, I do not want to follow Sarah's suggestion or inspiration from Sarah and split each summation on two parts. What if I really want to keep summation as it is written in the top line? So there is no science behind it. It's only math, how to redistribute factors, how to redistribute things. Any ideas? Okay, let me try to fix this stuff myself, and then we'll continue, because maybe I didn't express it too much, insufficiently clear. So I am opening brackets. Summation I goes from 1 to HOMO, then 1 from blue. Summation from J goes from 1 to HOMO times rho I J theta I theta J. Next term, I goes from LUMO to infinity. J still goes from 1 to HOMO. And then I put here rho ij theta I theta j. Now I goes from 1 to HOMO. J goes from LUMO to infinity. Rho ij theta I j. What will be the last term? So two summations I j. What I should go from? Steven, I see you are inhaling air. Is it to answer this question or for different purpose? You just wanted to breathe.
Yes, I believe I can answer the question.
Okay.
This would be the fourth term, which from the previous slide you showed was marked as EE. And so this would be
I goes from where to where? What are the limits for I?
limit 5. It would be this one would be LV, wouldn't it? Along with J?
So it should go from Luma to infinity, right?
No.
Why?
Oh. Yes.
Okay. And J?
This would be
Luma to infinity.
From Luma to infinity, yes. Yeah, thank you. Rho I, rho J, theta I, theta J. Okay.
Thank you, Sarah.
So we just opened bracket from line 2 to line 3, right? But here is the, so from this line 3, we do see, let me highlight. So this one originates from green. 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 And this one originates from blue. Right? So we are opening brackets. And by opening brackets, we do have 4 terms. And the main idea is that we need to account occupied and unoccupied orbitals separately. They will bring us different contributions, right? And based on this, we just chopped our summation, our limits of summation. But instead of chopping limits of summation, we can do slightly different thing. We can keep our summation as we used originally, so just 2 summations. But just a second. No, I shouldn't do it. I can tell that the part of the density that corresponds to indices of the I and J below HOMO will correspond to ground state only, right? Because HOMO and below correspond to ground state. The part where we start from Luma and end at infinity will correspond to excited state completely, right? So all orbitals here, I and J, are excited. And there are cross terms where one orbital goes from 1 to HOMO, another from Luma to infinity. And here is opposite, from Luma to infinity, 1 to HOMO. So one can call them, it is neither ground nor excited. So one can call it a hybrid or mixed excited ground and ground excited. I see raised hand. Yes, yeah.
So, Professor, the last part, why I'm not able to see? It's okay. I equal to LUMO and J equal to LUMO, right?
Uh-huh.
So could you please explain this one again? Right. I was just distracted.
Mhm. Are you agreeing that this summation from 1 to infinity can be chopped as two summations in different ranges, right?
Yeah.
So, and second summation can be chopped in the same way.
Yes.
Now it is algebraically, although typically we put in brackets like x and y, but we can also symbolic operation of summation or integration can be also placed in brackets. And we have product of two brackets, each of which has two terms.
Okay, now I understand. It's like a multiplication. It's
Yes, it's like a plus b
mhm.
times c plus d.
Yes. Okay. I got it.
Okay,
Okay, it's clear.
and then there is another function, and then we get like a, c, f, and so forth, right? Plus a, d, f, like total four terms. But here we are chopping contributions of this different contributions to ground and excited state. So the last part will correspond only to excited, the first only to ground, and middle two things something in between. Okay, so we just started to discuss the thing, and now do you recognize this expression? Yes or no? Okay, so thank you for confirming. So it is the same stuff which we just got by opening brackets. And the orbitals, they are once and forever. You compute orbitals and they're stored. But expansion coefficients are different. And we can arrange them in a matrix, right? Because they have two indices. So when both indices are more junior than HOMO, when they're small, here it is highlighted by yellow, it will correspond to ground. When both indices are more senior than LUMO, larger than LUMO, we highlight them in green, and they will correspond to excited. And when they are simultaneously, one index is below LUMO, another is above, one is below HOMO, another above LUMO. It's a transition density because it corresponds to transition from ground to excited. Whew. So here is the same expression. The goal, and I will I'm telling a little bit ahead of time. Later on, I will repeat it. If we describe the ground state, we have only rho GG. We have only density matrix for ground state. But if the system is being perturbed by external electromagnetic radiation, such as light, there will be populations of the GG, which corresponds to your fair V in last homework. Plus, in addition, there will be transition density terms. So if you, right now, I'm not asking if you okay or not okay with it because it's too early. I know it is counterintuitive information and I will go over it once from different angles. But the main goal of the theory that we are studying this month or this fourth chapter is how to find these densities as function of the incident light. Whether incident light will perturb density and creates some population in excited state and some transitions. So this little equation, this slide is, I do not believe it helps to any real computation and any real understanding. But if you will be talking to community of professional computational chemists, if you need to explain what you do later on, this is a really good explanation. So it is not for our understanding; it's more to explain what we do. So, Lola, would you please help me and tell which symbols you see in this equation?
I see total density,
Uh-huh.
density of the ground state, density of excited to the ground state,
Mm-hmm.
density of ground state to excited,
And what else?
and excited.
And what else?
I don't see this. Yeah, I don't see that properly.
So what are those? Can you guess?
I don't know what they are.
But
I can't see what this sign, like, is this mu? I don't know. I can't.
so it relates to the absorption spectrum and transition densities and how we were finding this. So in our procedure, we were calling this mu, we were calling it d. And it is hidden in the file oscillator strength.
Expression?
No, oscillator strength. So someone is typing.
OS strength file. Is that what you said?
Yes, it is in the oscillator strength file.
Okay, I don't know what that is.
D. That's okay. That's okay. Z. So, anyone wants to help? The question is, yeah. K is asking what is D. I want to ask you what is D. So, in some literature, this.
Yeah, like in our last homework, when you wrote that DIJX, IJY, it's remind me the like we did a calculation for absorption spectrum, absorption. Then when we saw the OS strength, more OS strength, then there is a like there are several columns there: oscillation, strength, transition, and dipole, then XYZ.
Stop, please stop. Now, everyone, please try to remember last 5 words that Kia told and try to answer the question. What is D?
Dipole?
Yes?
Dipole in X and Y and Z direction?
Those are Cartesian projection of what? Of which?
Dipole moment.
Dipole moment.
Yes, dipole moment. Okay, so it is dipole moment.
I was telling you stop me like
transition dipole. Yeah, thank you, Kay. You inspired everyone in the class. So Lola, you were checking what is mu. Mu is just I apologize, but in different textbooks, people use different letters. Sometimes D, sometimes mu. D because dipole, mu. I do not know why. People simply like the letter mu. Now, the energy, the Hamiltonian of interacting between light and material is written as minus mu, or you can put minus d, scalar product times E. where E is electric field, which like depends on time as T as initial value of this vector, and then it just cosine omega t. D omega t. So oscillating electric field is a light, right? And when the light is applied, then it makes this dipoles to follow the light as quick as possible. If the change of electric field is slow, then it will be just as compass. The dipole will follow electric field. But if it is really high frequency, then instead of quickly going forward, backward, electron tells, no, I do not want to rotate this way. I'll better go to excited state. And then it will be transition dipole. Make sense? More or less. Now, the question, thank you all for contributing to the discussion. The challenging question that Vola started to answer. In this line, we have that total density can be as a summation of ground, excited, transition density. But if you have practical situation when model is being excited by a light, the especially of light of low intensity, if this E is really small, E goes to 0. Then the change to the density because of the light will be really small. And people call perturbative, which means like small modification. And it will be for transition densities, it will be proportional to electric field or proportional to energy of interaction between light and matter in a linear fashion. But the excited state portion will be proportional to electric field squared. So if E was 0, here we will have 0 squared. So it will be like second order correction. Therefore, many methods for practical research just neglect this term and drop it because it is of secondary importance. And instead focus only on these linear terms. So only transition density, which is linear in electric field. So please ask questions or tell if something is not clear by this point. No questions means either everything is clear or everything is so unclear that even no one knows where to start. Yeah, thank you, Lina. Then show, okay, not okay, more comments needed. Okay. Yeah, thank you. Do not hesitate to offend me. I like when you do not understand something. It gives me a chance to be useful. So, Steven is practicing TDDFT on daily basis because of research group that he's attending. Lola is currently doing a rotation at the group. So what Steven is doing every day and Lola will need to do every day for next like few weeks is to practice TDDFT theory. And TDDFT theory is all about the transition density. So these little things. How the change to total density due to light is introduced. How the light changes density. And already in this theory, one assumes that light only contributes to transition density and neglects all other contributions. Okay. This one. This one. So next. It is my next ugly slide. So I will not ask you what you see here. I'll explain myself. But maybe I can expand. So here we are showing the density which does not depend on position. It's only density matrix. And we do have the segments. So in the red square, in the red box, it is ground. In this green color, it is excited. In yellowish color, it is ground excited. And in bluish color, it is excited to ground. So ground to excited corresponds to excitation. Excited to ground corresponds to emission. So these little symbols do have explicit indices, I and j. So each symbol has two indices, I and j. And in this red block, we have I equals homo, rho equals homo. I equals homo minus 1, j equals homo minus 1. You see? In the excited block, we have two indices. I equals lumo, j equals lumo. I equals lumo plus 1, j equals lumo plus 1. And we have this cross terms. So this is a lot of unnecessary writing. So if we would be without PowerPoint ugly notes, if I would need to deliver this material on the whiteboard, I will need to write all the symbols one after another. And those who wants to take notes, will need to write it in the notebook with too many symbols. So too much. Let's just oversimplify our consideration and look on the simplest possible example. If you have such molecule that has only one occupied and one unoccupied, so only homo and lumo, then our density matrix will be 2 by 2, right? And one element corresponds to ground density, one element corresponds to excited, and two elements correspond to transitions, right? So then the simplest density matrix will be just rho GG, EE, rho GE, rho EG. So now I can make it smaller. If we consider placing our molecule under oscillating electric field, before we apply electric field, only rho GG will be non-zero, will be actually 1, right? And as we start to apply electric field, oscillating electric field, there will be something non-zero in other terms. Okay? Dealing with electric field as function of time is really cool, but too expensive and not practical. If we believe that electric field oscillates by the same cosine function, then one can do Fourier transform Fourier. And instead of electric field as function of time, consider electric field as function of frequency. So please show if you heard about Fourier transform, never heard about, or you've heard the name but you do not know what it is. So I saw only, okay, at least one. If you listening to music and adjust your with equalizer, you can enhance bass, remove high frequencies, right? Make sense? So you can adjust the sound. So it means sound, which is also oscillations of like pressure waves, density waves, is converted into frequency. So Fourier transform is a mathematical operation that converts time into frequency or frequency into time. Signal that depends on time converts into signal that depends on frequency and other way. And the original derivations, original theorems for TDDFT were done for time domain, but practical implementation is done for frequency domain. So frequency. We are going from time domain to frequency domain. And the main question of the TDDFT theory is to tell how much the off-diagonal elements will grow as function of the frequency of the electric field. And let me bring a rational discussion on the basis of common sense. So if we do have this two-level molecule, this consists only of HOMO and LUMO. If we excited by a photon of a frequency that is bigger than HOMO-LUMO offset, molecule will be not excited. If you excite it with frequency that is smaller than HOMO-LUMO offset, it will be also not excited. In order to perform the excitation, the frequency of the light should be exactly equal to the energy offset. So H bar omega equal to energy of LUMO minus energy of HOMO. So one needs to match so-called resonant condition. Resonance condition. Right? So basically TDDFT implements resonance condition in mathematical way and connects it to density function theory. It tells at which frequency promotion of electron from occupied to unoccupied will happen most vividly. Slide. I will even type. Whew. So please tell any questions or agree or disagree with this statement. So,
Doctor, do you ask? We agree with the question as well?
if you agree with this statement, if it makes sense, or if it doesn't,
Yeah.
you need to find.
Yeah, I agree. I agree.
So, and this is main task of TDDFT theory. I do not need the word theory because T stands for theory. So, as a result of TDDFT calculations, the computer program where it is implemented will give the frequency number 1, frequency number 2, and so forth, at which the system will respond to photoexcitation. We did address same question in an approximate way in our file oscillator strengths. We have like first and second are orbital numbers, third is oscillator strength, and column number 4 is energy offset, energy of J minus energy of I, energy offset for pairs of orbitals. So the thing that you were practicing before by making absorption spectrum answer this question. So the data in column 4 tell at which frequencies your model, your molecule is able to be excited by light. But we will discuss on other meetings which approximations make our oscillator strength approaches not ideal, and which good things are done which good things are done in TDFT to make this calculation more precise. K is asking what is D. So this one dependent. And this 3 you already know, density, right? So time dependent. And I already got the positive comments from one of the faculty member who told like, oh, students remember something after your class. They told that time-dependent density function theory has nothing to do with time dependence. So if you were telling it to someone, then please accept my gratefulness. The wave of information reached me. So TDDFT theory was originally using time dependence in the derivations for taking electric field as time dependent and densities as time dependent. But upon Fourier transformation, it lost time dependence. But to make it a unique name, people keep calling it time dependent. But in fact, main answer from this theory is set of frequency or transition energies. Okay. So we are about to finish in a few minutes. I think I'm already overusing time. So let me bring a couple of comments on this ugly slide. So in the oversimplified model where we have only what? Okay. Let's go back from oversimplified. Let's still consider that we have full GE component, which will be like a matrix of 2 by 2. Now, working with matrices is cool for mathematical operations, But for data storage, if you're storing big files, it's not comfortable because you do not know how many columns is in your matrix. Like if you work with a large amount of data in Excel, if it is many rows, it is okay. But if number of columns is bigger than your screen, then it is discomfort, right? So there is a convention and agreement to store big matrices as vectors in vector form. So here we have this homo minus 1, lumo, homo minus 1, lumo plus 1, homo, lumo, homo 2, lumo plus 1 elements. So one can store them, symbolically store them as a column. So put first one in here, second one in there, third one here, and fourth one there. So it's still matrix in this example 2 by 2, but we save this as one column. Do you permit me to do so, or you will argue against it? Or you don't care? Is it okay? It doesn't, right? It's just format of saving. So if we accept this format of writing of the density matrix as a column, we will approach to the format that Gaussian software is using, and that TDDFT theory in its derivation is how it is written. So in the community of this time-dependent density function theory, instead of this three symbol notation, rho GE, they call it X and Y. So transition density for excitations and transition density for emission. So the byproduct of TDDFT theory is to find these transition densities as function of frequency. So main question, find set of frequencies. Second question, find transition densities for each frequency. And I think we are arrived to the end of the slides. And it's more than enough for today. Thank you for your attention and investing your time. Everyone is welcome to disconnect. I'll stay here to answer questions, and looking forward to meet you today in the lab.